Hello and welcome to this video on modeling and solving problems with similar figures in the problem. Now, two figures, two shapes, be it triangles, rectangles, rhombuses, pentagons, hexagons, whatever. Two shapes are similar, two figures are similar if they have all their corresponding angle measures are the same measure, or all their corresponding angle measures are what they call congruent, and also the ratio of corresponding sides is the same throughout the two figures, right? So the ratio of corresponding sides is constant. All right, there's a scale. It's like there's a scale factor involved. Alright, so we'll see what I mean here when I just have a couple examples, one just involving some triangles. Alright, just similar triangles here. So let's look at these. Alright, so my first example has to find the length of side xy, so that's this side here in this triangle, x to y. How long is that? Given that triangle, right, again this is a little symbol for triangle, right? Triangle MNP, so M to N to P, this triangle right here, is similar to triangle XYZ, so X to Y to Z. Now, another way they might put this, the triangle MNP is similar to, in some text you're going to see this little tilde symbol, little wavy thing. That symbol there means is similar to. Okay, that little tilde symbol. And then triangle XYZ. Okay. And what does that mean? Now how your figures are named is very important. When you say that triangle MNP is similar to triangle XYZ, pay attention to the way they're named. This means several things. Okay. It means one, something about the angles. It means all the if two figures are similar, then their corresponding angle measures are the same measure, right? Have the same amount of turning, they're congruent, they would say. So one, if MNP, triangle MNP is similar to triangle XYZ, you can look at how they're named, it matters. Then angle M, right? So this symbol here is a symbol for angle, just a little, couple segments here connected at a common vertex. Then the angle M would be congruent to, right? There's this little equal sign with the tilde above. This symbol here means is congruent, pardon me, is congruent to, right? That means it has the same measure, right? It's the same size, if you will, of an angle. So angle M would be congruent to angle X, right? Both the first letters in the name. And angle N, the second letter in this triangle name, would be congruent, have the same measure, to the angle Y, right? The second letter in that name. And angle P, right? The third letter in this name would be congruent to angle Z, right? The third letter in that name. And you might also see them indicated on the picture like this. And this is going back. These are some little this is like a little bit of geometry symbolism here. See a lot of geometry books. So if angle M and angle X are congruent, in my picture they might put like a little arc mark on angle M there, and angle with the vertex X there, to show that, hey, these both have a single arc mark. so they're congruent. And to show that angle N is congruent to angle Y. Now I'm not going to put a single arc mark again, because if I leave that as a single arc mark, it'll imply that it's also congruent to M, but nowhere am I stating that angle N and angle M are the same. So we'll throw a second arc mark. So now it's got 2 marks on angle N, and it is congruent to angle Y in this other triangle if they are similar. So again, 2 arc marks on the angle with a vertex of Y, angle Y. And then to indicate that angle P is congruent to angle Z, those have the same measure. Again, I can't use 1 or 2 marks anymore, because that would imply that they're congruent to these, and we don't know that, right? We only know that P is congruent to Z, so I'm going to throw a new symbol, one with 3 marks, right? 3 marks on angle P, and then over here, angle Z, the angle with a vertex of Z, also put 3 marks on it to indicate that those two are indeed congruent, right? So if that triangle is similar to that triangle, and they have named them this way, MMP, XYZ, then those are the corresponding angles, right? First letter to first letter, second to second, third to third. The corresponding angles are all congruent. All right. Now the other thing that implies, right, when they say 2 figures are similar, is that the ratio of the corresponding sides is constant, right? So the second thing that this would imply is, and again, look at how it's named. Now a side length, to form a side length, we need to take 2 of these letters, right? So, the side length M to N, MN, and side length NP. Right? So just again, make sure you understand how they're named. And the ratio of side MN, if you took the length of MN like this, the ratio of that side length, right, which is going from left to right here, M to N, to the corresponding side length in the other figure, right? I went first to second letter, M to N. I'm going to do the same thing here, X to Y. So the ratio of the length of MN to the length of XY, right? So this length here, which is 12 units, to this length here, which is what we're trying to find, that will be equal to the ratio of corresponding sides throughout the entire figure, right? Every ratio. So MN to XY will be equal to, and just keep on going here, the next 2 letters, N to P. Right, so this side here, N to P, that ratio to the ratio to the length of, and I went second to third letter, do the same thing here, second to third letter, Y to Z. Alright, so M to N over X to Y will be equal to N to P over Y to Z. But these will also be equal to, right, and every single ratio of sides are going to be equal, of corresponding sides are going to be equal in similar figures. So M to N over XY is equal to NP over YZ, and that'll also be equal to, now you could say P, if I go third to first, if I kept going here, I went M to N, then N to P. If I go P to M, right, P to M, 2, and I went third to first, so I'll do the same thing here, Z to X. All these ratios should be, and those are all the sides, right? There's only 3 sides, so there should only be 3 ratios of corresponding sides here as a triangle. So P to M, which has a length of 15, to Z to X, which is a length of 10, that ratio should be equal to that ratio, should be equal to that ratio. All the ratios of corresponding sides of similar figures are equivalent, right? Okay. So we're going to use that, right? You see how we have proportions here, right? I could set these 2 equal to each other, there's a proportion. I could set these 2 equal to each other, there's a proportion. Or I could just set these 2 equal to each other, there's a proportion. So we're going to use the fact that these 2 figures are similar and set up a proportion to find the length of the side they're asking us for. Okay. Well, what did they want, right? The question asks us for the length of side XY, right? That's the important thing here. find the length of side xy. So I'm going to set up a ratio, a proportion, in which one of the ratios has the length of xy, right, in the fraction, and I want that to be the only missing piece. Okay, so like if you look down here, if I were to just set this proportion up, mn to xy equals np to yz, set up that proportion, I know the length of m to n, 12. The length of xy is what I'm trying to find, and so that's unknown. And you could call that a letter or something, so I don't have to keep writing xy, but I'll just write xy. And then np to yz here, I do not know either one of those, right? I don't know either one of those lengths. So if I use this proportion, I'd have 3 missing pieces, and I can't do anything with that. All right, I want to set up an equation where I only have 1 missing piece. So it would have to be this ratio here. So here's the proportion I'm going to set up. Right, where you set 2 fractions equal to each other. The ratio of length mn to the length xy will be equal to, since they're similar, the ratio of pm or mp to zx or xz. Right? In this proportion, I will only not know the length of xy. And notice again too that if you remember, if you saw my video on solving proportions or setting up proportions in problems, notice how the numerators come from the same triangle, right? These both come from triangle MNP. And see how the denominators both come from the same triangle, right? From triangle XYZ. Right, those are lengths over here. And it's just like when in a previous video where I was solving proportions. When you're solving proportions, setting up proportions, I want the numerators to have similar units or have some sort of similarity to them, be talking about the same thing, and the denominators to also have the same units or be talking about the same thing, addressing the same thing. So both of the numerators are from the same triangle, right? Both of the denominators are from the same triangle, and that's what I want when I'm setting up a proportion. Alright, so now I'm going to fill this stuff in. The length of mn is 12 units, so 12 in the numerator, divided by the length of xy. Now again, you can call it a single letter, maybe just L for length. But I'm just going to keep it as xy and know that that's not 2 letters. That's not 2 variables, that's 1 variable. Okay, that's just the length of one side. Equals, and then the length of PM, P to M is 15 units, right? It's right there. Over, and then the length of X to Z or Z to X that distance is 10 units. Okay. Alright, and then we have this proportion to solve. I like to, you could do the, multiply the extremes and the means, do the cross products, and that's totally fine. But I like to simplify the fractions first and multiply by the LCD and all. I do the same steps I normally do for solving an equation with fractions involved. So first I'm noticing that 15/10 over here, that reduces, right? They have a common factor of 5. So I'd have 12 over the length xy. Again, that's technically a single variable, just one length, equals, and then 15/10 reduces to 3 over 2, right? This is 3 times 5, this is 2 times 5, you would cancel the 5s. Wonderful. And then the least common denominator here would be just the product. This is just one variable, again, just xy, and there's no other factors, and this is just 2. So that's the product of those two things, 2 times the length xy. Again, I'm going to put in parentheses because it's all just one thing, right? Maybe I should have just called it something like L or something for length, but. And then I multiply both sides by this length, by this LCD, sorry. So the left side I've got 12 over this length xy, and I'm going to multiply that by the LCD, 2 times the length xy, equals, and then this side 3 halves, and I'm going to multiply it by the LCD, the 2 times the length xy. And then you see some common factors, right? This has the length xy in the denominator, the length of xy in the numerator. So all I'm left with is 12 times 2 on the left side. This has factor of 2 in the denominator, factor of 2 in the numerator, so all I'm left with is 3 times the length of xy. Alright, so we have 24, 12 times 2 on the left, equals, and then 3 times the length of xy on the right. And then to get the length of xy alone, I need to get rid of this times 3. Right? So we divide by 3. Or multiply by a third. Right? Remember, division is the same as multiplying by the reciprocal. Over here, the factors of 3's will divide out. And you have the length of xy equals, and then 24 divided by 3 is 8. And there's your solution. Now, well, before I circled that, I should have said, let's check. All right, let's go back to the original proportion I set up. You know, this one here. Replace the length xy with 8. Is 12 over 8 equivalent to 15 over 10? Well, yeah, 12 eighths and 15 tenths would both reduce to 3 halves. You'd have 3 halves equals 3 halves. So, yes, you know, the 8 is a good solution here. All right, so back up in my picture, I can now say that this length over here from x to y would have to be 8 units if these two, they said these two triangles are similar, and if they are similar, that must be 8, because the ratio of corresponding sides, again, has to be the same in similar figures. 15 to 10 must be the same as 12 to, and this must be 8 then. Great. Alright, so that one there, we were given a picture, right? I was given a picture of two similar figures, and then, then had to set up a proportion and solve that proportion myself. And but it's not always the case that you're given a picture. Very often you might have to, in a word problem, you might have to draw your own diagrams or draw your own pictures, and then then set up your equations and solve and go back and see if it makes sense in the problem. So that's what my last example today is on. It's a word problem I pulled from some book, where we're going to have to set up our own picture and then set up a proportion, and we'll see similar figures here. So here, a tree casts a shadow that's 25 feet long at the same time of day, right? Now the only reason this is said here is so that the sun is in the same position overhead, right? And really it should say at the same time of day, in the same area, right? Not on a different part of the earth or anything like that. So at the same time of day in the same place, a 6-foot tall man casts a shadow that's 2.5 feet long. Okay. How tall is the tree? Okay, so here's I'm going to draw a picture of what's going on here. So we have the sun. Right, I'll say this is the sun up here, letting out some light. And then we have, here's the ground. Let's say, for purposes of this problem, just to make things simple, that the ground is flat. The ground is not hilly or bumpy or all over the place. Alright, and then I've got this tree. Now, I'm only going to represent the tree with just a green segment, right? So here's this tree, and again, just for purposes of ease, we're going to say that the tree is, let's say it's perpendicular to the ground, right? It shoots straight up. And, all right, here's, tree. Okay. And it says that this tree casts a shadow, right? So the light's coming from this way, so the shadow's going to be down here. All right, let me just do this. Here's this. So the top of the tree lights here, and then cast the shadow. Here's where the shadow is going. The light comes down. So none of this is getting hit by light. Right? The tree is blocking it. So it casts this shadow of 25 feet. Right, and that's again the shadow of the tree. Alright. Now they're saying at the same time of day, so the sun is in the same spot, and again in the same area, right? Not like miles away or anything, because you go farther and farther away, you get a different angle of the sun. You know, want the sun to be overhead at the same place as it is for the tree. We have a man, right? A 6 foot tall man. So I'm just gonna make that a like a brown segment here. So again, here's this, hopefully shorter than the tree here. So here's the man, and they said he's 6 feet tall, right? So I'll put 6 foot there. And again, the man casts a shadow. Sun's in the same place. Sun coming down, casting a shadow this way. So all this stuff here is blocked by the man. And again, I'm gonna make, just to make this thing easier for me, we're gonna assume the man is standing straight up. So perpendicular to the ground, 90-degree angles. That's what these little boxes mean, 90-degree angles to the ground. And this person's shadow is 2.5 feet long. Now I know my drawing is not great. You know, I said this is 6 feet and this is 2.5 feet, even though it looks longer. You know, this is not perfect, right? Not to scale or anything. I'm doing a hand drawing. If you want to pull out a ruler or something and make things nice, be my guest. All right. Now, we're going to see here that these two triangles are similar. So you see how they have the same, this angle is the same. And then I'm not going to get into all the geometry, but again, the sun is so far away. You know, the sun is like 93 million miles away from the Earth. So the angle at which these come in are the same as well. I mean, like it's a you know, even if the man were standing just 50 feet away from the tree, the difference in the angle that the sun is hitting them would be minuscule. So we're going to say that this angle here, right, the angle of the sunlight with the tree standing straight up, and because they're standing straight up too, that is a property of parallel lines, right? You know, the man is parallel to the tree, and we have the sunlight being like a transversal. These would be corresponding angles. Again, lots of terminology from geometry, transversals and parallels. Again, not going to worry so much about that. But this angle here and this angle here are basically the same, right? Again, the sun is so far away that that difference in angle is microscopic. All right, so angle, this angle and this angle are the same. And again, you geometry people out there, if two angles of a triangle are the same, are congruent, then that other angle, the third angle, must be congruent as well. All right. And so I have two figures with all congruent angles. All right, and if you have two figures with all congruent angles, two triangles anyway, with all congruent angles, then the figures are similar. All right, and I'll put that note up here. Again, this is when I make videos in the future about geometry or more geometry class related stuff, we'll obviously get more into this. But so two triangles that have all congruent angles. All right, so two triangles with, all three angles congruent. Again, the little symbols for triangles and angles with all three angles congruent, right? Again, the symbol for congruence, are similar. All right. In fact, you can just say with just two angles that are congruent, like we did, this angle and that angle, this angle and that angle, because if two angles of a triangle are congruent to the two angles in another triangle, their third has to be the same, because all three angles of a triangle add up to 180 degrees, so what's left over would have to be the same. All right, again, I'm not going to go into all that geometry stuff. I know I've probably said too much already, but just know that these triangles are similar. And I'm gonna label them. All right. So like in my previous example, these vertices of the triangle, these three sides here, the contact with the ground and the tree, the top of the tree, and where the shadow hits the ground at the end of the shadow, So I'm going to call this, maybe A, vertex B, and vertex C. We'll call this triangle ABC right here. So A to B to C. And then this same thing, I'm gonna label these vertices, where the man's on the ground, where the top of the man, and then the end of the shadow. I'll call these X, Y, Z. All right. And so this is triangle X. Again, I'm naming it in the same way I would name this one, with the corresponding angles the same. So angle A, I put vertex A first, which has the 90-degree angle on it. So I'm going to do vertex X first over here. Vertex B has the 1 tick mark. Vertex Y has that congruent angle, so I'm going to put Y next because I put B next, and then C is next there, which corresponds to Z. All right, and we're seeing, because of this statement up here, that my triangle ABC is similar, right? Is similar to triangle XYZ. All right, and since they are similar, right, that means that again, all three angles, all corresponding angles are congruent, and all pairs of corresponding sides come in the same ratio. All right. So because of this similarity, we're going to be able to set up a ratio, a proportion. I'm going to do that on the next page here. We're going to be able to set up a proportion, where we set two ratios equal to each other, so that I can find the height of the tree. Right? The question was, how tall is the tree? Now I don't want to write out tree or even AB. So what I'm going to do is I'm going to call the height of the tree T. Alright, so say the height of the tree is T feet, right? All my other units were in feet. So I'm going to say, I'll do this off to the side here. T represents the height of the tree in feet. Okay. Alright, so now, noting the way I name my triangles, they are similar, right? Because all three angles are congruent. And the height of the tree is length AB, right? And then AB, right, in this triangle here should correspond to length XY in the smaller triangle with the man. All right, so the ratio of AB to XY, right, that's first two letters to first two letters, should be equal to, and then I'm going to set up another ratio over here, where again my numerator is going to come from triangle ABC, and the denominator is going to come from triangle XYZ. I want the same numerators, the same kind of denominators, right? All right, so the only length I know in triangle ABC is this length here, the length AC or CA. All right, that's the first and third letter in my name of the triangle. So the ratio of AB to XY should be equal, will be equal, since they're similar, to AC, and AC corresponds to XZ, right? XZ, the first and third letter again in my name for the other triangle. So here's a proportion. I'm going to fill some stuff in, and then we're going to solve it. And then answer the question, it is a word problem. I should answer word problems in full sentences with units involved. All right. So let's fill some of this stuff in. All right. So the length of AB, that's the height of the tree. That's T. Right? That's T feet for the numerator on this side. XY. XY is the height of the man. All right. That's 6 feet. I'm just going to put 6. Because everything's in feet. No need to write feet all over the place. Alright, so that's the ratio on the left side. Equals, and on the right side, AC is 25 divided by, and then the denominator is XZ, and XZ is 2.5 feet long. Okay. Now again, I like to do a little simplifying here. Now this one, it doesn't involve as much because you see I already have 1t. I just need to get rid of this divided by 6. But the other side, you might notice that 25 divided by 2.5 is just 10. right? Isn't 2.5 times 10 the same as 25, right? So that right side's pretty easy to simplify. So I've got t over 6 equals, and then 25 divided by 2.5 is simply 10, or 10 over 1 if you want to keep writing it like fractions. And now to get rid of the divided by 6, get that 1t in the numerator alone, I would just multiply both sides by 6, right? That'll cancel these common factors of 6. And then do the same thing to the other side, times 6. So I'm left with t here equals, and then 10 times 6, 60. And then double check, go back to the original, put in 60 divided by 6 is 10, and 25 divided by 2.5 is 10. Both ratios are equal to 10. Fantastic. So the height of the tree is 60 feet. This is the answer, but I want to write it out though, right? Because there should be units on here. It's a word problem. You have to answer a question. All right, so the actual final answer to the question of how tall is the tree is 60, and remember t represented the height of the tree in feet. Everything was in feet. The tree is 60 feet tall. And this here in the box, this is how I would answer this if I was given this as an exercise in a math class. Alright, any word problem, you should be answering word problems in complete sentences with units involved so that the numbers actually mean something. Right? The numbers actually make sense. Now in some word problems, sure, units aren't mentioned, so wouldn't worry about it there. But most word problems you're going to come across, most application problems, units are involved, so use them. Okay. So again, this was just a couple examples where you're seeing two similar triangles, and whether it be similar triangles, similar rectangles, similar octagons, whatever, the same rules for similarity hold. Two figures are similar if all their corresponding angles are equal, and again look at how they're named, pay attention to how they're named, and the ratio of all the corresponding side pairs is always the same. Alright, and as always at the end of these I like to say, try your best to get the material, understand the material on your own first before looking for help. I have found that most people tend to remember things, or things stick better with them if they've taken the time and the effort to try to understand it on their own, and they feel more proud about it. So read through the author's material, read through the author's examples. Sometimes maybe even try to work out the solutions to an example before you see how the author did it. See if you can learn from mistakes there. And practice problems in the backs of a section or on a worksheet, what have you. Make sure you're doing ones that you can actually find answers for. Maybe look in the backs of books or wherever they're provided. Try to find ones that have answers provided so you can check yourself. And just don't give up after the first attempt at a problem, right? Don't give up right away. Don't get so frustrated so easily. Keep at it. If after several attempts it's still not working out, walk away from it for a minute. Go read the material again. Maybe there was something you missed the first time that'll hit you the second time through, or maybe even the third read through. Something will click with you that didn't click the first time. Who knows? But if after that, several read-throughs of the material, several attempts at a problem, it's still not clicking, you're still not getting it, it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. Ask a teacher, a tutor, a friend, someone else in the class who knows the material that might be willing to help. Look for materials, supplemental materials on the subject online. Find videos, such as this one on the subject, or other videos out there that are plenty better than this one. I promise you, they're out there. You can find them, and just keep at it. Stay persistent. Keep practicing. Never give up, and I know you're going to get it eventually. I promise you. And also, try to go into these things with a positive attitude. I know that's easier said than done. Most people out there, they think, oh, I hate math. I've hated math my whole life. And if you go into your homework and your exercises with that mindset, well, guess what? You're probably going to continue to hate it because you've already determined in your head that you don't like it. If you go into it with a more positive attitude, thinking, I might learn something from this, I might take something from this, I might enjoy myself, this might be fun, it's going to be fun to learn something, fun to do something on my own, with my own hard work, then you'll be surprised at how much of a difference a positive attitude can make. So keep at it, keep practicing, try to have fun, and thanks for watching.